Okay, conditional propositions and logical equivalence. Okay, so we're going to look at things called conditional propositions. So here's an example. So that the dean has announced that he says, if the math department gets an additional $60,000, then it will hire one new faculty member. Okay, so this is an example, right? Statement 1.13, right? This is a condition that is a conditional proposition. So here's our definition. So if P and Q are propositions, the proposition if P then Q, right, is called a conditional proposition and is denoted by this, okay, right here. So the proposition P is called the hypothesis, right, and the proposition Q is called the conclusion. So let's look at this example right here. So in the one above, we have the following. P, the math department gets an additional $60,000. That's either true or false. It's a proposition. Q, the math department will hire one new faculty member. That's either true or false. It's a proposition. So if we're going to think about this here and try to arrive at a reasonable truth of the conditional based upon the truth of P, truth and falsity of P and Q. Okay. So what's the deal here? Okay, I'll just sort of go through this real quickly with you. So I'm just reading this. Okay. Then the proposition 1.3 assumes the form of 1.32, the hypothesis statement. Okay, so the math department gets an additional $60,000 and the conclusion, right? So that's the hypothesis, and the conclusion is the statement, the math department will hire one new faculty member. So here we go. What the truth value of the dean's statement is, right? First, suppose that the math department gets an additional $60,000. If the math department does hire an additional faculty member, surely the dean's statement is true. Okay? In other words, if they get the money and they hire another mathematician, then the dean's statement is true. All right, let's see here. On the other hand, if the math department gets an additional $60,000 and does not hire an additional faculty member, the dean is wrong and the statement is false. Okay? So now, suppose that the math department does not get an additional $60,000. All right, so they don't get the money. So in this case, the math department might or might not hire someone. Okay, new faculty member. Maybe they hire somebody because they're replacing a retiree or something like that, right? So on the other hand, the math department might not hire someone. Well, you know, that's fine too, right? Surely we would not consider the dean's statement to be false. Thus, if the math department does not get an additional $60,000, the dean's statement must be true, okay? And here's so based upon that little discussion, that's how we interpret the truth values of the conditional proposition. So P implies Q is defined by the following truth table. Notice here that if P and Q, if they're both true, then that statement is true. If if P is true and Q is false, then the statement P implies Q is false. If, notice down here, if P is false, regardless of the truth or falsity of Q, it is the statement P implies Q is true. So, okay, let's just move on here. Let's take a look. I have some examples I want to look at here. So, okay, here's an example. Let P be the statement 1 is greater than 2, and Q is the statement 4 is less than 8. Then P is false and Q is true. Okay. Therefore, P implies Q is true. Right? Because why? Because P is false. And the statement Q implies P is false. Why? Well, because Q is false and P is true. Okay. Let's look at another example here. Assume that P is true and Q is false, and that R is true. Find the truth values for each proposition. Okay, let's do a couple of these. So P and Q implies R. Let's think about that. Well, P is true, and so you have to the last statement. This is always going to be interpreted last. Okay, in other words, you might think that what, yeah. So let's, okay. In other words, here, take a look at it here. So P or Q, P and Q. Well, since P is true and Q is false, P and Q is false. So therefore, P implies R is true, right? So we just have to really, let's check out this one here. P or Q. Well, P or Q is true because P is true and Q is false. So since that's true, I have to look at not R. Now it says R is true, so that means not R is false. So number B has to be false, right? Because we have something that is true implying something that's false. Now over here, notice this is where they've put the brackets here. So let's take a look at this statement. Now, let's see. Q is false and R is true. So no matter what, this statement here is true. And P is true. So P and this is true. So this statement is true. C is true. Now let's look at the last one. P implies, let's see. Well, P is true. Okay, implies Q implies R. Now, what does Q imply R? Q is false and R is true. So Q implies R is true. Therefore, P implies Q implies R is also true. Okay. Okay, so here's a little note, is that a conditional proposition that is true because the hypothesis is false. We usually say that that's true by default or vacuously true. Just something we say. Okay, oh, this is kind of important. So let's go through this. This is the idea of a necessary condition, okay? So let's look at D here in this example. I'll take a look at this, D. A necessary condition for the Cubs to win the World Series is that they sign a right-hand relief pitcher. So what's a necessary condition? So a necessary condition is just that, a condition that is necessary for a particular outcome to be achieved. In other words, if they want to, there's no other way, that they must do that is what the idea is. Okay, now here's another thing that we want to talk about, a sufficient condition, okay? And that would be coming from example E. So let's see what that all has to do with. So it says, the statement is, a sufficient condition for Maria to visit France is that she goes to the Eiffel Tower. Well, clearly, right? I mean, if she goes to the Eiffel Tower, she's already in France. So that's sufficient. If she goes to the Eiffel Tower, she's already in France. So that would be sufficient to just go to the Eiffel Tower. And that's what they're saying, that a sufficient condition is a condition that suffices to guarantee a particular outcome. Okay, let's take a look at this. Hold up. So here we go. Definition. If P and Q are propositions, the proposition P, if and only if Q, is called a biconditional proposition and is denoted by P. Then you have these double arrows, Q. Okay, so this is how that is defined. P, Q. If they're both true, then that's true. If one's true, it's false. False. If they're both false, it's true. So this is, they're called logically equivalent, right? A biconditional proposition is denoted by this. Okay. Let's take a look here. So here we have the, here's the idea here. Definition. So suppose, I guess I misspoke a bit up here. Let's take a look. I guess, well, maybe I haven't, but I sort of jumped the gun. So let's take a look at this. Yeah, never mind the thing about logical equivalent. I was speaking out of turn here. Here we go. Definition 1.3.10. Suppose that the propositions P and Q, right, are made up of the propositions P1 through Pn. We say P and Q are logically equivalent and write P3 arrows Q, provided that given any truth values of P1 through Pn, either P and Q are both true or P and Q are both false. So let's look back up here. Is that satisfied by this biconditional? So it's true. Watch this. If that's true, then both of them were true, right? If it were, so there we have something. True, they're both false. Okay, so I guess that does satisfy the definition of logical equivalence. All right, let's give an example. This is called De Morgan's law of logic. We're going to verify the first De Morgan's law. That is, that these two statements are logically equivalent. So not P or Q, they're claiming, is logically equivalent to not P and not Q. Okay? And then the other one is P is not P and Q is logically equivalent to not P or not Q. So it's sort of like the distributive law of the not sign, except you have to change the logical connection to and or. Let's see if it's, in fact, they're logically equivalent. So what do we do? Well, we see that the two things that are being used in here, two propositions, are P and Q. So we write down all the possible truth values for those things, and we just check. So if you check with P true and P true, you would get false for this because you would have P or Q would be true, and not P or Q would be false. Now you look over here to this one. If we have both true, then that would make not P false and not Q false, so that'd be false. So you can go through these and see that these are the truth values that you arrive, and notice that they all they agree everywhere. So that makes them logically equivalent. Let's see. Let's do this one. Show that the negation of P implies Q is logically equivalent to P and not Q. Okay, so here's the solution, right? We basically look at this and we look at the truth tables of those two things that are supposed to be logically equivalent, and we verify that, in fact, they agree everywhere. Well, let's do the first one. True, true. So true implies true. That makes it true implies true is true. So not that is false. True, true. True, and this would be false. That would make that false. If you do that for all of these, you will see that they agree on every assignment of truth values for P and Q. So those are logically equivalent. Okay, let's see. I wanted to do maybe another example. Okay, here's something that's kind of important. You'll hear this term quite a bit once we get down to trying to prove things. Some of you will use this quite a bit. The conditional proposition P implies Q, and it's contrapositive, not Q implies not P, are logically equivalent. Okay, so here's the proof of that fact, and now you can see it. Right, you can check that these truth values correspond to, like, true, true. Right, let's do this one. Let's do this one. False, true. Okay, if P is false and Q is true, let's see. Well, then if P is false, that's automatically true because it's a, right? It's a, it's true because we know that for such things, if P is false, the whole thing is true. Okay, let's look at this. So if P is false, let's see, that makes this true, right? See that? So if P is true, that's true. And if Q is false, then not Q, if Q is true, then not Q is true, false, and we know that anything false that implies, and that is true, so that's correct. That is true. Okay, so that's it. Okay, we're done with 1.3. I think this will help you with solving some of your homework problems on 1.3. All right, thank you. If you have any questions, refer back to this video for sure.